All right, number 4, which reaction's faster? So again, we have an alkyl chloride, a tertiary alkyl chloride, same reactant. Tertiary alkyl chloride. So the leaving group will be chloride. The carbon the leaving group is bonded to is tertiary. It's bonded to 3 other carbons, right? That guy right there. We're losing a leaving group and we're making an alkene. So this is an elimination reaction. Same starting material. What is the base? If it's an elimination reaction, there has to be a base. DMF, T-butanol, potassium T-butoxide. So again, potassium T-butoxide is this guy. Strong base, localized negative charge on the oxygen, sterically hindered. All right, it's sterically hindered, so it's a poor nucleophile. You already know we're doing an elimination reaction, but potassium T-butoxide would have let you predict that we're doing an elimination reaction. The base is the same then in both cases. Potassium T-butoxide is the strongest base on the board. So again, anytime you're working these problems, you want to identify what the strongest base is, the best nucleophile, best leaving group, the best electrophilic carbon. So strongest base is potassium T-butoxide. The only difference is in the solvent. All right, T-butanol versus DMF. I've drawn the structure of DMF there. T-butanol is that. And so this is this gets down in the weeds a little bit, but SN2 and E2 reactions are favored in polar aprotic solvents. So I'm going to erase this. I'm going to erase all of this. All right, so aprotic, this causes some consternation among students. What does that aprotic mean? A polar aprotic solvent. An aprotic solvent is one that can't donate hydrogens in a hydrogen bond. Okay, so clearly DMF has hydrogens. It's got methyl hydrogen, it's got the H on the carbonyl, but none of those H's are on an electronegative element, so they can't donate in a hydrogen bond. T-butanol, on the other hand, does. That hydrogen can hydrogen bond, and what happens is you form a hydrogen bond between the hydrogen bond donor and the negative charge on the base. So T-butoxide is the base. If you think about the mechanism, sorry. Gotta grab a beta hydrogen. Boy, I'm botching this. All right, the mechanism, T-butoxide is going to donate electrons to this proton. The electrons in the CH bond make the pi bond. Chloride takes the electrons in the carbon-chlorine bond. These electrons have to be donated. The electrons on the oxygen have to be donated. If those electrons are tied up in a hydrogen bond, they're less available to be donated. So if the solvent can hydrogen bond to the base or the nucleophile in an SN2 reaction, that'll slow the reaction down. So because DMF can't donate a hydrogen in a hydrogen bond, this bottom reaction is faster. Right? The bottom reaction is faster because the solvent doesn't hydrogen bond to the base, whereas in the top reaction, T-butanol does hydrogen bond to the base. So this is a difference in solvent. Polar aprotic gives faster E2 and SN2 than a polar protic solvent.